Hello, this is a video on, I call it the colligative properties. It may not be said, it may not be pronounced like that, but that's how I call it. There are actually three colligative properties: boiling point elevation, freezing point depression, and osmotic pressure. However, I don't usually talk about osmotic pressure in first year chemistry, but I replace it with another one, which is called Rauolt's law, which actually is not, by definition, a colligative property, but the reason why Rauolt's law is the way it is due to the same physical process that the colligative properties are. So I'm going to remove the osmotic pressure and replace it with Rauoult's law. And the Rauoult's law, this handout here is on boiling point and freezing point. Rauoult's law handout is right here. And the main issue with colligative properties in Rauoult's law is, how does the physical properties of a solvent compared to the physical properties of a solution? In essence, when you add in solute, what physical effects does it have on the solvent to make, so therefore you have a solution? And in general, what happens is the solute particles get in the way of the solvent particles. That's an unscientific way of saying it, but physically, that's basically what's going on. So, if you're going to boil something, remember, the boiling point is the temperature at which the vapor pressure of the liquid equals atmospheric pressure. In essence, you're trying to get a specific number of solvent particles into the gas phase, because they're going to hit the wall, which equals pressure, and there's a certain number of hits you're trying to get to called atmospheric pressure. So, if your solvent on the surface is just solvent particles, then all those particles are going to hit the wall when they get in the gas phase. However, when you start adding in solute, some of the solutes sit on the surface of the solution. So therefore, they have now replaced some solvent particles that will have to go into the gas phase. So therefore, if you think about it, you need more energy, because now you have solutes in the way. So to get us that solvent particle that is now underneath the solute particle, it must go around the solute particle to go into the gas phase. So that requires more energy. So therefore, more energy means higher boiling point. Or another way of looking at it is, once you start putting in solute particles on the surface, that location is no longer available to have a solvent particle go in the gas phase. So you have less solvent particles in the gas phase at any given temperature, therefore the vapor pressure must be lower, therefore you must you must go to a higher temperature. And the more solute particles, the higher the boiling point will become for the solution. So it's all about the number of particles. Now, there's something else. It's called the Van Hoff. That's V-A-N in space Hoff, Hoff effect. It's not only the substance, it's the base unit or the particle, because that's what's on the surface. It's getting in the way. So therefore, that is included in it. So you don't look at the compound, you look at the base units that are getting in the way. And we will talk about that in a future video. So it's boiling point elevation. And you can remember the elevation because it's always from the physical property of the solvent to the physical property of the solution. The solution boiling point is always going to be higher than the solvent's boiling point because there's solute in the way. Similarly, so it's an elevation. That's how you remember it. Now, for the freezing point, it's the other way around. It's a freezing point depression. And this is an example of what water looks like when it's going to freeze. And what happens is the solute gets in these spots right here. And what they are they're now in the way from this water and this water interacting with each other. And if these two water particles can't interact, liquid particles can't be solid particles, because it's the formation of these, what are called lattices, that cause the ice to form. So therefore, what you would have to do is you would have to slow all of the particles down, because if there's a solid particle here, it needs to be pushed away. And the more soluble particles, the more they have to be pushed away. And remember, they're moving, so the slower they must become. And you can't just slow the soluble particles, you must slow all the particles. So the more soluble particles you have that are in the way, the slower you must go to get them out of the way. Therefore, the slower everybody is, meaning temperature is lower. So therefore, that's a depression. That's why it's called freezing point depression. So the solvent's physical property is greater than, in this case, freezing point, is greater than the freezing point of the solution. And the more soluble particles you put in, the slower you have to make everybody, so you can push all the soluble particles away when the solvent particles are linking together to form the solid. So it's a depression. Remember, always for colligative properties, it's always solvent properties to solution properties. So therefore, that's why it's freezing point depression. So your solution, basically your solution's freezing point is always going to be lower than your solvent's freezing point. And your boiling point of the solution is always higher than the freezing point. Now, the colligative property, the other property, which is vapor pressure, it's kind of like boiling. It goes right along with boiling. The vapor pressure of the solution is always going to be lower than the vapor pressure of the solvent, because, again, the solute particles are in the way of some solvent particles to get in the gas phase, to get a vapor, and the vapor exerts pressure. So you have less vapor particles in the gas phase, causing less vapor pressure. Again, this is Rauolt's law, and it's not technically a colligative property, and there's more to it than that, but for first year, that's good enough. Okay? Now, besides the Rauolt's law, because that mathematical equation is a little different, and we're not going to do that this year in first year, you can do mathematics to freezing point and boiling points calculations. And it's basically the same equation, except your change in temperature for boiling goes from the solution's boiling point minus the solvent's boiling point. Because remember, this in boiling, the solution's boiling point is always greater than the solvent. So your delta T will be a positive number, and it's always positive. So how much of a change is there? Well, it's a function of two things. It's a function of a constant, which is, in this case, the boiling point elevation constant, which is unique to the solvent, not the solution, but the solvent, and the molality, m bar, of the solution. Because remember, molality is moles of solute over over kilograms of solvent. So the more particles you have, the higher number m bar will become. Therefore, the greater the difference in temperature, in this case, the boiling point elevation. Therefore, once you know what delta T is, then you can find the solution's temperature by T solution is equal to delta T plus T solvent. And the freezing point is, oh, one more thing, that constant is a value found in the book, and that's why it's a B for boiling. There's a exactly similar calculation for freezing point, except it's KF, freezing point, different constants, but the same molality m bar in there. And the temperature equation is different, because the change in temperature, this delta T has to be positive, and as you know with freezing point, the freezing point of the solvent is always greater than the freezing point of solution. So that's why it's solvent minus solution now instead of the other way around for boiling, because this delta T is positive. So therefore you can use that equation. So we give an example here. It's a boiling point, so it's solution minus solvent. Okay. Let's see. Yes, we don't use this equation actually anymore. We actually break it up into two distinct equations. So you're not going to be able to use this equation right here. You need the molality, moles of calcium chloride per kilogram of H2O. So you find that to be, that's the moles. You know how many, you know what the kilograms is. So here's your molality, and your delta T is equal to the constant you find in the book times the molality to give you the change in temperature, delta T. So delta T is T solution minus T solvent, which changes to T solution is equal to delta T plus T solvent. You know, it's the solvent's 100 degrees C for boiling point of water, and here's your temperature change. So the boiling point of solution is 100.35 degrees C, which, yes, I know I'm breaking the sig fig rules, but it's not a very big change. So I needed to break the rules so you could see the change. Okay, so that's how you do the calculations. Again, you're not making it one equation. You're keeping it as two different equations. Okay, and again, the Rauolt's law, we're not going to do the math on that. So an analogous way of doing it is for freezing point. You just use the freezing point equations. So this is how you do it if it's mathematical. Okay, so in recapping, colligative properties is all about the solute is now going to get in the way of the solvent doing something. So there is a physical property difference between just the solvent itself and the solution you make. Thank you.